All right. Good evening, everyone. Thanks for joining for today's session. Um, so what we will do today is we will solve three questions. Last week, I think we solved like 4, 5 questions, and it took a lot of time. So I tried to condense the matter that I wanted to discuss with only three problems today, so that I can effectively convey it, so that it will not be a waste of time for you also, while not compromising on the quality. Okay, so we will be focusing on week two's uh, content, and but feel free to ask me any questions even for week one and week two if you have any. And I hope you will be submitting week one assignments soon. So all the best for that. And if you have any questions related to that, that also I can answer. I cannot solve the questions for you because it's an assignment. If you have any doubts, or if you want to clarify something, I can help you with that. Uh, all right. So if there are no questions, let's get started for today's session. I will be finishing these three problems in another 40 or 50 minutes, and then later, whatever questions you have, I'll be happy to answer. All right. Um, Now we have like four students. Thank you very much for joining. Let's start today's session. All right. So in week two, um, what we saw is we continued our discussion on conduction equation. We tried to, so if we solve the conduction equation, it's a differential equation. We all know that, second order differential equation. And if we want to solve that, we need some initial conditions and boundary conditions. So that is what we started with our week two, if you have gone through the lectures. And after that, we did some simplification. We simplified the bigger heat conduction equation into a 1D steady state heat conduction equation, which means we told that the heat is transferring only in one direction, and we simplified it further, assuming that there is no heat generation, and then we also did certain problems with heat generation. And I hope your week two problems is going to be with heat generation, so uh, you need to take that into account. Okay, so while doing this process, we also saw that this heat flux can also be uh, can be an analogy, can be seen as an analogy compared to electrical circuit, right? So like in electrical circuit, we have in resistance and conductance. Similarly, in a heat transfer analysis, you can also have resistance and conductance. And this heat resistance that we talk about will actually simplify our problem in terms of solving a certain problem. So this thermal resistance, drawing a electrical circuit equivalent to equivalent electrical circuit for your thermal system will actually be very beneficial, not just for solving this particular problems, or not just for using in this particular uh, course, but it is also actually widely used in industries, in terms of systems modeling. So most of the in chemical engineering plants and other places, usually they do systems modeling, and this systems modeling they use electrical circuit equivalent of all the thermal and fluid power systems. Okay, so this is the basic start of this is the basic place. This is a place where you get introduced with these concepts, and in future, in fluid mechanics, also in fluid power systems, also you will get more concepts on conductance and resistance, and that will lead you to industrial professional, where you can apply all these concepts over there. So make sure that you understand this concept. Make sure you uh, uh, use it as much as possible, and we will solve one or two problems in that concept. Okay, and that was our week two content. Now let's solve the problems I have. So the first problem is actually one of the problem that I gave last week, which I couldn't solve, partly because it is not fully covered in the lectures, and also we didn't had time last week. Okay, so today I'm going to solve this problem. And let's read the question, and you are going to help me solve this problem also. Okay, so the question goes like this: an one-dimensional plane wall of thickness 2L is 100 mm. So there is a one-dimensional plane wall experiences a uniform thermal energy generation. So there is a heat generation in it. Okay, with 1000 watts per meter cube, and it is convectively cooled at x equal to plus or minus 50 mm. Okay, so there is a convective cooling, there is a heat generation in the wall, and the temperature of the fluid is 20 degrees Celsius. If the steady state temperature distribution is T of x equal to A times, this is actually L square. For some reason my keyboard is not writing it, that's why I wrote it like this. So L square minus x square plus B, okay, where A and B are given. What is the thermal conductivity of the wall and what is the convective heat transfer coefficient is what they are asking. Okay, so first let's try to visualize the problem. So the problem is something like this. So one dimensional plane wall is there. Okay, let's consider this as our one dimensional plane wall, and you know, usually everything is 3D. So for your visualization, I'm also drawing it as a 3D, but we are interested only in this direction, x, let's say. Okay, and now what they are telling is this plane wall has a thickness of 100 mm, but they have said it's 2L. So probably they are expecting us to put the um, you know, the coordinate system at the center of the uh, plane. Okay, so these are some of the cues you may need to know or you may need to remember while reading this question. So it is something like here, and our x actually starts from here. Okay, and
That's a good point.
yes, Basant, you
Actually, the origin is taken to be at the midpoint, so that one
right,
side is plus x and another side is minus x.
right, yeah, very good, that's right. So the total length here is 2L, which is 100 mm, and as Basant said, this is going to be minus 50 and this is going to be plus 50. Okay, all right. And so what are the other things given is this has a heat generation of 1000 watts per meter cube. That is important. So let's write it down separately. 1000 watts per meter cube, and 2L is 100 mm, which means L is 50 mm, and T infinity is given, which is 20 degrees Celsius, and T of x is given. This is the temperature distribution in the solid worlds. So it is written in terms of x, which is the coordinate system. Okay, so A times L square minus x square plus B, where A and L are given. So A is 10 degrees Celsius per meter cube and B is 30 degrees Celsius. Okay, so this is actually your temperature distribution. Usually what we will do is we do not know the temperature distribution. Luckily for this problem we know the temperature distribution. Okay, when we don't know, we just solve the equation to get it. Okay, let's see how we are going to do here. um, and what they are asking is they are asking us to find what is the thermal conductivity of the wall, whatever this wall is, and what is the convective heat transfer coefficient. You can just call it H. So these are the two things you need to know. So where is convection happening, right? So here
Sir,
it,
once
yes, yes, please go ahead.
A is 10 degrees Celsius per meter square, right?
Oh, sorry. Yeah, it's my bad. You're right. Thank you very much. All right. Yeah, my bad. So, now the convective, ambient fluid is also cooling the solid wall. So solid wall is generating heat, and it is going to the ambient heat is going to cool this solid wall. That's the entire problem is about. So where does this cooling happen is both at x equal to plus and minus 50. Okay, so which means you have a cooling like this over here across this wall. So probably let me use a different color. So this is the wall. This is the front face of the wall, and similarly we have a back face also. Both sides you have this air which is going around, air which is going to cool this with the T infinity and H. Okay, these are the two parameters that's been given. So and basically we are supposed to find what is this H. Okay, so wall is generating heat and it is the air is cooling the wall. That's the thing. And we have to find out, we the temperature profile is given, we need to find K and H. So that's the question about. I hope the question is clear for everyone. So if not, please stop me. It was if you read it you will understand, like mostly everyone understands, but I just want to give you the picture more carefully so that you do not miss certain steps which usually we take it for granted. Okay, all right, I hope everyone is clear. So now we need to find K of wall and H. How do we find? Anyone have any idea?
Actually, first of all, we have to do the energy balance.
Okay, okay, we can do energy
So,
balance. And
so from that, because since the same quantity of actually energy coming in plus energy generated is equal to energy going out.
right, okay. um
So
so
the equation to follow is dou by dou x into k into dou t by dou x plus qg, that is the generation, or we can say it is q, that is 1000
so you can,
watt per meter cube.
yeah, it's better we use QG itself. Okay,
Uh-huh. So that should be zero. Since it is one dimensional and taking,
so when you say energy balance, where do you apply this energy balance? So it has to apply across a control volume, right?
yeah,
Yeah,
correct.
what would be your system basically?
So our system in here, the system includes the convective region
So
that is at the surface, both the surface.
you mean to say, let me you mean to say this whole thing is your system,
Yeah,
right?
yeah,
Yeah, that's right, that is true. So we can draw this as a system, and as you said, you can draw a energy balance. You can take a one dimensional approximation. So let me
yes,
write it
one
down.
do.
Let me write it down. So the assumption is like 1D approximation, and then we can write it as a steady state so that heat stored will be 0. Okay, so
Yeah.
basically as you said, you can write it like E dot in minus E dot out plus E dot generation is equal to E dot stored, and you can say this is 0, and you can write this in terms of heat flux, and then you can make 1D approximation, and finally what you get is, so basically what you will get is you will end up having 1D steady state heat conduction equation. So that is exactly what we derived in our class. So
Yes,
basically,
correct.
instead of starting from E dot in minus E dot out, I'm going to take uh, a step forward, and I'm going to start from 1D steady state heat conduction equation. Okay, so with heat generation. So basically, we all know. So this is what gave us what you call the big formula, like rho c dou t by dou t equal to you know, in a vector form it's like del square t plus qg, right? This is what, if I I think there should be a k here. K times del square T plus Qg. This is what we got from this, from when you do this energy balance. This is how we derive the energy equation, right? This is a most general equation. You can use it anywhere. Okay. While you have to make sure that K is a constant, and what was the other thing? Only heat conduction is happening. So similarly, in this case, we are going to assume that K is constant. Only heat
Constant
conduction
area,
is happening.
constant area.
Huh. Well, this is generalized. Yeah, constant area, that is true uh, for this problem, but this equation is generalized. This equation, as I wrote, this is in vector form. So this del square is a Laplacian operator. So you can write it as you can write it in three-dimensional form. That's what I'm trying to say. This is a three-dimensional form. So you can write it as del square T. Uh, so this is the most general form, where T is a function of both x, y, and z. So you can write it as x square, y square, and z square. Okay. So this doesn't require a constant area approximation. Is that clear? This is the most generalized
Yeah.
form.
Yes, yes, sir. Yes, sir. Yes, sir.
Okay. Okay. So so this is the most general form. This doesn't require any constant area approximation at all. Now when you take 1D approximation, as you said, as you rightly said, then this becomes a constant area approximation. Okay. And with k constant. Okay. That is also one more thing. So k constant. So we made all this approximation, and then when you say steady state, sorry about this, steady state, then this becomes 0, and then when you make 1D, this becomes 0, and then finally what you will have is d square T by dx square times k plus qg equal to 0, or you can write qg by k. Okay, this is what we derived actually with heat generation. This is the heat conduction equation we have. So what we can do is, like Basant Jana said, you can start from E dot from this, but you can do all these calculations by yourself, like we derived in the class. So if you remember back in class, what we did, we started here, like he said, and then we did all these things, and then we applied Fourier's law, and then finally we got this, and then we need to express this energy, and then finally we end up with this equation. And once you got this equation, you apply steady state heat conduction, and then you will get this equation, right? So what I'm going to do is, I'm going to take a shorter approach. I'm going to directly start from that steady state heat conduction equation, and you are also recommended to start that, because we are going to deal with Cartesian coordinate system, and uh, it's a plane wall. So we are going to have a constant area system. So we can start with 1D heat conduction equation. Okay. So I hope this clears where to start the problem, where do you start to solve it. So since we make this assumption, we can directly jump into a steady state heat conduction equation, and we can solve this problem. Okay. Is that clear?
Okay, sir.
All right. So if that is clear now, so anyway, okay. Now I'm going to start from solving here. Um, Now how do we can we wanted to find this k. Okay. So we are interested in finding this k. Okay. We know qg. We know qg, which is already given. Now d square T by dx square we can find out, because
Right, sir.
temperature profile is already
X is given.
uh, x is also given.
Yeah, yeah,
Also temperature profile is also given. So
yeah,
we
yeah.
need a function to differentiate the temperature, right? So this is the temperature. This temperature profile that we have here is what tells how the temperature is varying here. Let's say this is the x-axis and this is the temperature axis. It tells that the temperature varies something maybe like this. I'm not really sure. I'm just plotting a graph.
Might be since it may be parabolic since it contains a square term.
Exactly. Yeah, it is parabolic. And also I think this is not the only side the convection current is going to happen. So this side also it's the same convection is happening. So I expect the temperature to be same on both plus x minus 50 and x plus 50. So that's why I draw something like this. And heat is generated inside, which means temperature inside the wall should be very high. Okay, so which means at the at the both ends of the wall you have cooling, so temperature is going to be lower, and heat generation is inside the wall, so temperature is going to be higher, and temperature profile given as x square as he rightly said, so it's going to be it is most probably will be parabola, and hence that's why I draw this profile. Okay, so probably we can write this as ts and probably maybe t naught, maybe something like that. Okay, so this is the temperature profile. This is how it varies within the wall. Okay, at every x position of the wall, this is how it varies. So we know that, we know the field. So what we can do is we can just differentiate it twice, and we get the we can get the d square t by dx square. Okay, so that is how we are solving the first thing. The first one is to find k. What is k? So we know t is supposed to be a is 10 into L square minus x square plus B is 30. Okay. Now you differentiate it once. What would happen? dt by dx. So L is a constant. X is the variable parameter which we are interested in differentiating with. So it's going to be 10 times minus 2x, and this is a constant. So I no need to teach you differentiation. You guys all know already. So I'm going to go ahead and do the differentiation. By the way, you guys also can carry out this calculation parallelly and let me know if you know the answer for k. Okay. Now you can differentiate it next time. Then it becomes simply minus 20. Okay. Now what you do is you just simply substitute it here. It becomes minus 20 plus qg by k equal to 0. This has to be satisfied because it's an heat conduction equation which comes from energy balance. So energy balance has to be satisfied. All right. Now k is nothing but you can write this as qg by 20. So I think qg is how much? 1000 watts per meter cube divided by 20, which is going to be um,
50.
50. Thank you. 50 watts per meter Kelvin or watts per meter degree Celsius. Okay. All right. Now the second problem, we need to find convective heat transfer coefficient also. Now let you guys tell me how would you find. Now it's an interesting problem.
Now we have to treat it as a composite wall having two convective heat transfer from both the sides, and the middle one in the material.
Hmm.
So it is conduction. The heat transfer is being conduction, and from both the sides it is convection.
Okay,
So
but
we'll
hmm
and so to generation is given. Okay.
but heat generation is also there, right?
Heat generation.
So
Heat generation is also there.
and
Right.
it is not at some point, some location. It is at entire solid wall. So uh,
Exactly.
resistance may not work there,
Here the resistance method work.
right?
So that means the heat flux is not constant throughout the wall. The heat flux cannot be treated as constant. They
Heat.
mean that.
So this is a steady state problem, right?
Uh,
If
yes.
it's a steady state, heat flux is still constant, right? So you think about it like this. This is steady state. Temperature is not going to vary with respect to time, which means none of them is going to vary with respect to time, right? Which means
Yes.
whatever heat is generated in the wall will be carried out by the convective currents at both sides. Whatever heat you generate, that is also constant. The heat is continuously going to generate. It is not varying with respect to time. Heat generation is continuously going to do. And whatever the air circulation that is happening, it's going to continuously do the same thing. And so the temperature profile does not vary with respect to time. If the temperature profile doesn't vary, your heat flux also doesn't vary. Heat flux also will remain constant, right? So when you mean constant, I'm thinking in terms of time. Uh,
No, no, no. What I mean is, heat flux can vary with respect to space,
it can vary. It can totally vary. That is true. That is true.
because of QG.
Exactly. It is true. Heat flux can
Ah,
vary with respect to space. I'm sorry.
okay,
You're
okay,
right.
okay.
So I was thinking in terms of time. However, with respect to time, none of them varies with steady
Yeah,
state,
fine, fine, fine.
right?
Thank you.
Yeah, you are right. So heat flux vary with respect to space. That is one complication because of heat generation. So now, how do we go about solving this problem? We need to somehow find out what is the edge, right?
Dutch. Okay.
So anyone have any idea? Do you guys want to pitch in? What would be the way to solve this problem? So there is no, complicated things. You guys no need to think more complicated. It's all boils down to one simple, uh, you know, uh, uh, what do you call one simple formula, or it's not even formula. It's one simple principle. So at the end of the day, everything is energy balance. So whatever the question I ask, your answer can be energy balance. Okay. So I gave you the part of the answer. So the answer is energy balance. Only thing is you need to say where this energy balance is applied. So with this in this course at least, we only deal with energy balance. So whatever the question I ask, the answer is going to be energy balance. But where you are going to apply will, if, with that you can actually find out what is H.
Sir, you just said whatever heat is generated by that wall is carried out by the air.
Correct.
So that is the energy balance. What I
Right.
feel is.
Right. But where will you apply this energy balance? So we need to think a little carefully. So there is some Q out going in, right? So yeah, you are right. You can say that whatever Q generation is happening is equal to H, right? So that is what you are telling. Let's do that. So energy balance is whatever heat generated. So that's a good point. Whatever Q dot generated. Um, Now, this Q dot is generated for a volume, right? So then we need to multiply by volume. What volume will you apply? So it's going to be volume of the wall, right? The entire wall. But we are going to say it's a constant cross section. So you can write it in terms of per unit, what do you call, uh, per unit area, right? So then you can write this as Qg into 2L, okay, times area. So because it is 2L times the side surface. So basically, how will I do this? So you have this wall. So this is the wall. This side is heat conduction. This side is also heat convection. This side is also heat convection. This entire thing is generating the heat. Now this heat generation is per unit volume. So if I want to know the absolute value of heat, then I have to multiply this heat generated, because it's watt per meter cube. I have to multiply with this volume. So now I'm going to say this is 1D conduction, and I'm going to say it's a constant area. So what I'm going to do is I'm going to write this per unit area. So basically, you can either multiply with area, or you can just remove the area, and this area is going to be same for both convection also. For convection also you have this area, right? So then what you can write is this is equal to H times Ts minus T infinity. But now this is front side, this is back side. So you need to write 2. Okay, 2 times H into Ts minus T infinity. Is that clear? How did I write this? So this is
I think,
yes.
sir, the area has to be considered somewhere on the left side.
Okay, yeah. You consider what I'm going to do is I'm going to write AS. but this side it's watt per meter cube. Okay, so to avoid confusion, let me write it down. This
No,
side
sir.
is
I am talking about because since QG is for unit volume,
mm,
Q dot G is for unit volume.
mm,
So only we have multiplied it with thickness only 12.
correct. So what we should
What
do,
about the cross section area, sir?
right?
So,
You also need to multiply by the area, right?
right, sir.
Right. So now both sides you have area, so you can
Right, sir.
basically remove that.
Okay, right,
Okay,
sir.
so that's what I meant by per unit area basis. Okay, so you are right. So what I can do is I can simply write this as, so QG is for per unit volume, and the volume means you need to know the extent of the, this wall, which is not given. So I'm assuming 1 unit is a 1 meter cube is the wall area. Okay,
Sir,
perpendicular
one
area.
more doubt, sir. Sir,
Right,
one more doubt. That
right.
is, here heat transfer is due to the generation of heat inside the wall. It is not due to the temperature difference because temperature is kept constant at both sides as TS.
Correct.
So there is no because of temperature difference there is no heat transfer. Heat transfer is only due to the heat generation. That is why we are able to write this equation. Am I right, sir?
Um, you are partially right. You are partially right. Um, because we do have a temperature profile and there is a temperature difference, and the only way heat transfer can happen is because of temperature difference. Okay, so you generate heat, but that will reach to increase in temperature compared to the surroundings. Then, since you generated heat over there, it has to dissipate. So heat transfer happens from high temperature to low temperature. That's the mechanism. Now, in this case, as you said, you are generating heat in this whole block, but still the heat transfer happens from the wall to the air, and that is due to temperature difference, right? So Ts will still be at higher temperature compared to air, T infinity. So there is a temperature difference over there, and that causes the heat transfer, the convective heat transfer. So you are partially right in terms of solid wall, but there is still a temperature difference from the surface of the wall to the what do you call, air. Is that clear, or did I confuse
Yes,
you more?
yes. That
Okay.
means if the walls are kept at different temperature, then we should account for the heat transfer due to that difference also.
Correct, totally right. So if this
Ah,
is at TS1 and if this is as TS2, you have to do a different temperature.
okay. Thank you, sir. Thank you, sir.
Yeah, you're right. Okay. So from here, what I'm trying to say is, from here it is going to be go to T infinity. Similarly, it is going to be going to T infinity. And this heat transfer is due to temperature difference. Okay. So now, as Basan said, what we are going to do is we are going to write this as Ts minus T infinity, and we have two walls, front and back, so we multiply it by 2 in times the area. But what we know is we are going to, these areas are same for both, for in this both, in left hand side and right hand side, so we can basically uh, remove them, so we no need to use it for calculation. Okay, so now what will happen, you can also remove this 2. Okay, and then you already know QG, so you can find H. How much is the H coming out to be? So we know TS also. Do we know TS? Now that's a good question. Do we know TS? So we can write this as QG times L divided by TS minus T infinity. T infinity is given, which is 20 degrees Celsius. Do we know TS?
Temperature profile is given now, sir.
Yeah,
10 into
wonderful.
L square minus, so
Yeah.
x can be, what is it? X,
X can be plus or minus 50.
so
So
just,
you can do plus 50 or minus 50. You can, but both will give you same temperature. Okay, let me do that also, so that it will be clear. So if you put L over here, what happens? So basically 50 is L. So these two will get cancelled, right? So ideally you will have only B. Whether you put L or minus L, it doesn't matter. Okay, so temperature would be simply B, which is 30 degrees Celsius. Okay, so let it be either plus or minus 50, which is also plus or minus L. Is that clear, We have the temperature profile. We are just substituting the x in
Right,
it.
sir. Right, sir. Right, sir.
Yeah, and then we got 30. Now what you can do? Oh, I'm sorry. What happened? Yeah. Now what you can do? You can substitute them, and what is the h you are getting? So q dot g is 1000, and L is 50 which is 0.05, divided by Ts, which is 30 minus 20, which is 10. How much is this coming out? It should be straightforward. I think 10, 100 times 0.05 is 5. Is that
I
right?
think 5.
Yeah. Okay. So this is way in which, as Mahadev Prabhu said, this is what we get. Okay. This is perfect. This is also one of the way, but there is one more way. Actually, I was thinking in that way, but once Mahadev said, I totally agreed that it is also one of the way. So I derived it, and it gave us this answer, and this is actually right answer. So there is also one more way you can do it. Can you guys guess how we can do it? The same energy balance I'm talking about, but you can apply it in a different place, and you can still get this. You guys want to take a guess? So you can view the heat transfer. So this Okay, let me explain it to you. So this is the energy balance that we did. So this is the wall we had. So actually it's kind of like a phone. You can view this as a phone. The phone also generates heat anyway. And okay. So this is what we have. This is what our entire plane wall is, one dimensional plane wall is, and I have drawn with some extensions. And then what we did was we actually constructed our control volume, or you can say control surface, whatever it is, or our system of study in this entire control volume, and we saw that this volume is generating heat. Okay, that is what is in the right side, and from outside you have air going in and out, air touching the surfaces. So that is the convection, this thing. Okay, so this is what the energy balance we applied for the whole entire wall, and then we got this answer. Okay, is that clear? So this is the heat generated, is what is getting convected away, because these are steady state. This is a steady state problem. Now what you can also do is you can apply energy balance for the surface. So for one of the surface, what you can do is, let me draw you that. You have this front surface. Okay, so now whatever heat comes to the surface is the heat will leave. So that doesn't matter whether it is a steady state or anything. Surface doesn't have a property to store heat. Okay, surface only has whatever E in comes in, E out goes. So for a surface, if you want to write energy balance, E dot in minus E dot out equal to 0. There is no E dot generation, there is no E dot stored, because surface is, you cannot store the energy. That's what it means, convection. So the convention is like that. Now for this surface, which is, let's say I am talking about the front surface. Okay, so let me call it the front surface at x is equal to plus 50. If you do energy balance, so what is the, if you do energy balance for this, you can still get the h. That's what I'm trying to say. Okay, what would be the energy balance here? What would be the E in and what would be the E out, if you guys want to guess, for this surface?
I think the energy coming to the surface should be, since the generation is 1000.
Mm-hmm.
So I think 50% will go to one side and another 50% is coming to other side.
Mm-hmm.
So that will
That
be 500.
that is right. That is right. But That physically, if you think intuitively, that is right. But what would be the so in terms of heat transfer, you need to talk, right? Because we are studying heat transfer. In terms of heat transfer, what is the heat transfer mechanism that is giving in heat, and what is the heat transfer mechanism that is taking away the heat
Okay,
from the
okay.
surface?
So it is conducting. The heat transfer coming in is conducted. The out is conducting.
Exactly. So you can simply do energy balance at the surface. So E in is, as you rightly said, the conduction, and E out is actually convection. So how will you do conduction? So Q conduction is minus K dt by dx at x is equal to 50 times area you can put, or you no need to put, you just put a flux, is equal to h times Ts minus T infinity.
T
Now,
infinity.
right. Now you know the temperature profile. We have already differentiated. When we differentiated, what happens? It was minus 20x, right? So if you put this minus 20x, k into minus 20 into 0.05. So please note that this is 50 mm. So I converted into meters. So is equal to h times Ts minus T infinity is 30 minus 20, right? Now k is, we already found it to be 50. So if you substitute this 50, what happens? 50 times 20 times 0.05 divided by 10 is equal to h. What is this h? This is again 100 times 0.05, 5 watt per meter square Kelvin. Okay, so you will exactly get the same results. So only thing is, you need to understand energy balance is true everywhere, and you need to apply it properly. And if you apply it properly, your problem is solved. So heat transfer is as simple as that. The whole entire heat transfer is, that's it. Okay. Only you need to know energy balance and where to apply, and did you account all the energy correctly. Once you know that, you are master of the heat transfer. Okay. Is that clear how we get the same edge from a different perspective?
Right, sir.
All
Correct.
right. All right. If there are any question, you can let me know. You can stop me anytime. Let's speed up the process. The second one is a no-brainer. Uh, I just put it here to uh, to quickly solve this problem, and so that the main reason to put this is for the thermal resistance. Okay, so let's see. um, Here, consider a composite wall that includes 8 mm thick hardwood siding, 40 mm by 130 mm hardwood studs on 6.5 meters centers with glass fiber insulation, and 12 layer gypsum with the wall board. So basically what they are telling is, this is your insulation wall that they are talking. What is the thermal resistance associated with the wall? Having 10 studs. Okay, so this is the composite wall that they are talking. Initially you have wood siding, you have a insulation, you have a stud in between, because insulation cannot stand like that. So I think because of uh, you know holding up the insulation, they have this stud, and then you have a wall board. Okay, so this, if this is your composite wall, and everything is has its own thermal conductivity, let's say simple different thermal conductivity, then what would be the effective thermal conductivity, or what is the thermal resistance associated? Okay, you can find the effective thermal conductivity, or you can also in this question they are asking, what is the effective thermal resistance, what is the resistance that you provide for this when you have like uh, like this wall for 25 meter, so 2.5 meter high and 6.5 meter wide. Okay, so which has 10 studs like this, like this, and each has 2.5 meter height. Okay, now there are two conditions given. One is, assume surface normal to the x direction or isothermal, which means this is your x direction, this is your x direction, and whatever is normal to the x direction are all isothermal, which means whatever the temperature in this point is same along this direction. That's what it means. Okay, is that clear? This is one condition. And the second condition is, assume surfaces parallel to x direction are adiabatic. So you need to think whether these two, what they are talking like. So if whatever is parallel, they are adiabatic, they are telling, which means heat does not cross in the perpendicular direction to x. Okay, are these two conditions same? What do you guys think? Okay, you guys are thinking too much. What we will do is we'll go ahead and solve for first one. Let's try to understand. Then we will get an idea. Okay. So the first thing is, um, we have like multiple material coupled together. So basically, we need to find the resistance. So that if you want to get the equivalent resistance, you need to draw something called thermal circuit for this, right? With all the resistance. Now the first thing is it is isothermal, which means across the x direction the temperature is same. Okay, which means you can assume it's a one-dimensional, and the heat flux is constant along the x direction. Is that right? Yeah, it's 1D steady state, right? So any questions till now?
No, sir, no, sir.
Okay, so if you want, we need to do this isothermal thing. Okay, and let's see if I can, let me draw it separately so that it will give you an idea. So there is this stud. Okay, and this is just an insulation. Now what they are telling is it is 2.5 meter high and 0.6 meter wide. Okay, so I am going to draw this side as height 2.5 meter. Okay, so it extends like this side is 2.5 meter, because they said the stud's length is also 2.5 meter, each with 2.5 meter height, which means stud has to go throughout the height, right? So I wrote drawing it like this. And so since we said that we have like 10 such system, 10 studs, so this entire length is going to be 6.5 meter wide, and the thickness is, I guess, initial thickness is something like wood siding is 8 mm, and then this whole insulation is 130 mm, and this part is how much, 12 mm. Okay, this part is 12 mm. So we have like 130 plus 12 plus 8 mm as the thickness, 2.5 meter height and 6.5 meter wide. Okay, now we just need to find the thermal resistance. For that we need to draw equivalent thermal circuit, and we said it's 10 studs, so it's going to be, so this part, whatever the part I draw, it's going to be 10 times repetitive. Okay, so first let's try to find thermal resistance for this part, and then we will extend that to 10 times. Okay, so for this part, if you want to draw a thermal circuit, how will you draw?
So about the 10 studs, having 10 studs,
Right.
each of 2.5 meter high.
Hmm.
So, okay,
So what I'm trying to say is, I'm going to say that this
after
part,
that
whatever
is,
we have here,
uh-huh.
is just copied over along this direction. So I have multiple these high sections,
Okay, okay.
like 10 times. So which
Uh,
then I will have 10 studs in between, right? So this is the first bar. This is the second thing. And what I have is these studs. This is one, this is two, this is three, like that till 10 I have. And the wide is 0.6, sorry, 6.5 meter. Okay, and the length along this direction on the plane perpendicular to the paper, perpendicular to my iPad, is 1.5 meters. Is this clear now?
2.5.
Or
2.5.
sorry, 2.5 meters. Sorry. Is this clear now? So the stud will extend along the 2.5 meter direction. That's what they say. So height means maybe I should draw it in a y direction, then it will be easier. But I hope this clears that out. Okay. Um, yeah, so if I want to draw, so what I'm going to consider is I'm going to consider this one section. Let's say I'm considering starts with the stud and then ends before the second stud. So if this is the section, and if I want to find the resistance for this wall of this section, resistance of wall section, okay, how would I do that? For that we need to draw thermal circuit. And how would the thermal circuit look? So you have wood sliding, WS, you have stud, you have insulation, you have wall board. Okay, four different materials. But the thing is, it is not seriously placed. Some place it is also parallel. That's the only difference. So for example, let's say a heat comes from one side of the wall and it goes to the other side of the wall. How it goes? So this is the heat which comes from this side, okay, and then it goes out in this side. If it is going out, what would happen? The same heat flows through the wood slide. So that is fine. There's no problem. Now, when it goes here, some part of the heat, okay, so let me draw a stud over here so that it will be clear. So in this, some Q1 heat goes through the stud and some other Q2 heat goes through the insulation. And after that, what happens? These two heat comes together and it flows through the wood board Q and then goes out. Okay, is that clear?
Yeah, yeah.
Right. Now, um, now only thing is the Q came and then it divided into two streams, which means you have to consider this as a parallel uh, circuit, especially between stud and the insulation. If so whatever the Q comes, so whatever the current, so in electrical terms, when the current comes, if it goes through the resistance, then it's fine. If it is does two resistance, then the current divides and goes, right? So here the current is heat basically. So if I want to draw equivalent thermal circuit, so initially you have some temperature at the other side. Let's say I call it Ti, and let's say I call this side as To. Okay, so initially I will be at Ti, and from Ti I have some Q coming in, which is Q, and it first goes through the wooden slide, wood siding. Okay, that is what it goes through. So I have certain resistance for this wooden side, and then what happens is it can either go through stud or it can go to insulation, but there is no option. It has to go through in both of this section. So what happens is this Q basically divides into two streams, and then part of it goes through the stud and part of it goes through the insulation. Okay, some Q1 goes through the stud, some Q2 goes through the insulation, and once it goes through, everything combines together and then goes through the final part, which is wall bore. Okay, and then it gets out this Q. Okay, so this is the equivalent circuit, thermal resistance circuit. And what would be the thermal resistance? Let's say if I want to uh, so what are the things given? So okay, K is not given. Let me provide you K. So you can either take from the book or I have it here with me. I will just give it the K. K of wood siding, first is wood siding, WS, is 0.094 watt per meter Kelvin, and K of stud is 0.16 watt per meter Kelvin. I forgot to give this in the question. And then you have K of insulation, which is 0.038 watt per meter Kelvin. And then you have K of wall board, which is 0.17 watt per meter Kelvin. Okay. Now, what would be the resistance of this wood siding? And this is RS, this is R insulation, then this is R wall board. What would be the is that clear? How did I draw the circuit? If there is any question, please let me.
Yes, sir.
Okay. I hope everyone also understands the same. Now, we need to find RWS. How do we find RWS? So we already know it's going to be L by Ka. Now, L divided by Ka. Now, only thing is L should be length of the wood siding, K should be, and area should be area of the wood siding. That's for respect to L and L, K, and A should be used. Now, the L here, what does it refers to? So this is the wood siding that we have here.
Thickness. The
Exactly.
thickness.
Wonderful. So this is going to be thickness of the wood siding, which is given to be 8 mm thick. Okay. So let me write down LWS is 8 mm. And then what else is given? Insulation is L insulation is 130 mm, which is also same for stud. And L wall board is 12 mm gypsum wall board. Okay. Now we also need to find area. Now the area for this repeating unit is somewhat less, but you can do this for the entire area also. For here we will just do it for repeating unit, because if you want to do for entire area, you have to draw this thermal circuit 10 times, and you have to do this. You have to solve this a big, not solve. I mean, you have to use this big equation, and then you have to find the resistance. So that's why we took a repeating unit. And if we know the repeating unit's resistance, the 10 studs is going to be just parallel of this repeating unit resistance. So you can just apply parallel logic for that bigger resistance, equivalent resistance, and you can get the uh, total resistance of the wall. Okay, let's see. Let's do it so that it will be clear. So now area of this is going to be, what would be the area of this? So you have one stud, you have one insulation. So one studs with this 40 mm, okay, and then you have 10 of that, which is within these 6.5 mm, 6.5 meters. Okay, is that clear? So then, who will I draw? I'm running out of colors. So this is 40 mm, and I have 10 such this, which means 400 mm of stud in your wall, and remaining is going to be insulation. So in 6.5 meters, if you remove 4 meters, then it becomes 6.1 meters. So 6.1 meters of insulation you have, 400 millimeters, which is 4 meters of stud you have, and both if you divide it by 10, one becomes 40 mm, and the remaining becomes 6.1 meters divided by 10 is 0.61 meters. So insulation is 0.61 meters. So and both of them corresponds to 0.65 meters, right? So in this, from the stud to this part, is I'm going to call this as, how much I'm going to say, 0.61 meters. Now 0.61 plus 0.04 is 0.65 meters. That's one repeating unit, and you multiply by 10 times, you will get 6.5 meter. That's what I'm trying to say. Okay, and this is the thickness. This is I mean, it's not, in this case, this is the width, and then the height is going to be 2.5 meters. That is going to be your area, which is uh, going to be responsible for the heat flux. Heat flux is going to cross that area. 40 times 0.6, 40 plus 0.61 times the 2.5 meter. Okay, so I know this is a little bit involved in terms of understanding what is the area across which heat flux is crossing. So I'm telling it's 0.6 0.65 times 2.5 meters for this wooden sliding, because that is the entire length of this one wooden sliding is 0.65 meters. Okay, so now you can simply substitute these numbers over here and you get the resistance of that, okay, which is going to be 8 mm 10 power minus 3 divided by K of wood siding 0.094 times 0.65 times 2.5. Okay, this will be the resistance of wooden siding. You can calculate it right now and you can write, or I will leave it up to you. So this is one, and now you have RS and RIN. So let's try to first find out resistance to stud, which is going to be same formula, LS by KS AS. Only thing is you need to find what is AS. Now what is the AS for here? LS we already know. LS is this width. This is across which the heat is transferring. So this is the width. This is the L, which is going to be 130 mm here, 130 mm. Now you just need to find the area. Area is going to be just this 40 mm times the 2.5 mm. This is the area across which the heat is transferring through the stud. Okay, heat flowing within the stud. So if I want to try this is going to be 130 mm divided by stud's thermal conductivity is 0.16 times area of the stud is, how much is this? 40 mm times 2.5 meter. So it is going to be 0.04 times 2.5. Okay, this is going to be your resistance through the stud. Now resistance to insulation, L insulation divided by K insulation times area insulation, which is going to be, L insulation is going to be the same areas, same uh, length across which the heat is flowing, but now it is going through insulated region. So if it is insulated, whether the heat flowing through that will be large or small? So basically I'm asking, you have this Q coming in and Q1 is going in this direction, Q2 is going in this direction. Now Q1 and Q2, whether either Q1 is greater than Q2 or Q2 is greater than Q1. What do you guys think?
So it depends on the insulation. Just let me say.
Right. So I'm telling the insulation, K insulation is
More,
less.
more, more resistance, less current or heat transfer.
Okay, so more resistance, that is fine. But if I say K, in terms of K, if you want to say, now let's say area is, yeah,
Uh,
I mean, you are
uh,
right. You are right. Yeah, you are right. I'm sorry. So I was thinking differently. I was thinking if the area is same, if area is same, you can also, now area in L is already same. And if the
okay.
area is same, you can say in terms of K, right?
Because we have converted into resistance power.
Right, right, right. So as you said, whichever is more resistance, the heat transfer through that is going to be less. That's what it means.
Yeah.
You are right. All right. So let's write the final resistance also. RWB, and RWB is going to be LWB by KWB and area WB. Now what is LWB? It is going to be thickness of 12 mm, 12 into 10 power minus 3 divided by K of the board is 0.17 times area of the board is going to be um, same as area of the wood sliding, because these two are, so this is sandwiched in between these two. So whatever the wood sliding, same areas are going to take, which is going to be 0.65 times 2.5. you can find all these three resistance, and then how will you find the final resistance? Let's say if I want to get resistance of this wall of one of the unit. So we have 10 such units. How will you write this resistance? So you have, how will you write the effective resistance? Now we have the circuit. What would be the total resistance? How will you write? We have two resistance in series and one resistance in parallel. First, you may need to find the resistance in
We have to
parallel.
convert the two parallel resistance into a single
Right,
equivalent single.
right. And then all series are there. Series resistance, you can just add them.
Add, yes.
Right, wonderful.
Yeah.
So what I'm going to do is I'm going to take one step further. Just going to write the final RWS plus there is this R parallel which is going to be which is going to look something like this.
It is 1 by
Right, 1 by RS plus
plus
1 by
1 by
RS
the insulation
plus
plus
RWB.
RWB, right?
Okay, wonderful. So this is your resistance of one section. Now how will you do it for other all the 10 units? How will it vary? So let's say R dash what? So this is for one section, right? So one section we have.
Right, right.
So now
There are 2 more units, 10 more
10 more
units.
things are there. So now what I'm going to say is, so we have like a very big wall and we replace this one section of the composite wall with just this one R wall. And what we have is 10 such things. So you have 10 such R walls. Okay. And heat is entering here and heat is leaving here. So you have 10 this thing.
10. So it is 1 by 1 by.
Right, right. That's all. So it is going to be one. So you have 10, right? So you should have um, 1 by, how will this be? Mm, so so our wall is for one area. So you have 10 such area.
Yeah. So first of all, we have to calculate the per single one, single unit.
Hmm. So you have 10 R wall. So it is going to be 1 divided by 1 divided by R wall
Plus
plus 1 by R wall, like that, like that, like that. You
same
will
thing,
have,
10
right.
times.
So it will be simply, you can replace it with
10
10
into
by R wall,
right,
right?
right.
So this becomes R wall by 10.
Yeah.
That's all. So you find R wall and you find this thing, and this becomes R wall by 10. So what I got is, maybe you can check whether this is right. I'm prone to make all the algebraic mistakes. So you can check for yourself whether I'm right, whether I'm doing right or wrong. 0.1854 Kelvin per watt is what I got. You can do the math and you can check. Now the question still remains. We did something, okay? But here they are telling that they assume the surface normal to the x direction or isothermal. Is this the same thing that we did now, or is it something different we did? Is my question clear? So, did we assume the
Temperature in uniform temperature. Isothermal means uniform temperature.
right uniform temperature? So, did we assume that even temperature is uniform along every section? Which means you can check here. When we cut here, we are seeing one Q, and we are assumed that temperature is uniform. When you cut, that's the point. So everywhere here, we assumed the temperature is uniform. Okay, so that's what this means, which means, I mean, the temperature is same along the cross section. That's why we call it, it's an isothermal thing. Okay, isothermal assumption. That's what this means. We assume the surface normal to the x direction are isothermal. Now, if you are not assuming that, okay, you are assuming the surface parallel to x directions are adiabatic, then what does it mean? How will it change?
Adiabatic means there is no heat transfer at all.
Along the adiabatic means not in this direction, it's along the
Ah,
cross section. So this is the x direction, x goes like this.
yes.
Now along this I don't have any q,
Okay.
this is 0. Along this direction I have this is 0, is what I'm telling.
Assume surface parallel to the existing.
So now how does this change your circuit? Will it change the circuit first of all? What do you guys think? Yes or no? Will it change this circuit?
Parallel to x direction is it will be a 2D conduction, right, sir? It
Parallel
will,
to, right, it will be 2D conduction.
but that is not our.
That has not been discussed here, right?
It will change. It won't change.
It won't change. Okay. It's
Sorry, if I'm wrong, please.
no. You are
I
totally,
think
you are welcome to be wrong. It's I'm not going to do anything. You should be wrong, then only we will learn. Everyone will learn. I should also be wrong. So don't be bad about uh, you, whatever you get in, whatever the idea you get, you just tell. Then only we can learn. So I encourage you to say there is nothing called wrong. So you can, this is what the understanding we have, right? So as you rightly said, it becomes a 2D problem, right? Then it becomes like uh, we are not even discussing in this, say in this course or nothing. But you can still make one assumption, which I'm going to say. Okay. Now it lies in this queue. So how you view this queue is going to be different now. So now from this region to this region, if you look at it, you have queue coming in, and then what I'm telling is some of the queue goes here, some of the queue goes here, is what I'm telling, right? Now when you do that, uh, but this can happen only if queue can move sideways, right? So because queue is coming in, this can be distributed only if queue moves sideways. What I'm going to say is, whatever queue comes in, it comes in as q1 and q2. Okay. So instead of this coming in, let me draw a separate so that you can understand. So now instead of q going like this, let's see. So q cannot go sideways at all. So which means if I have a stud there, and if the stud dictates that this is the q1 that is going in, then whatever I have up or down doesn't matter. Whatever q stud needs, that will be provided by those sections. Okay. Let's see if I can convey what I'm trying to say correctly. So this is q1 and this is q2. There is no change in that. Whatever the stud q goes in the stud, q goes in the insulation, there's no change in that. Now whether the heat present going through here and here, are they combining or are they going separately, will change. Okay. Now if I say there is no heat, if I say that along the surfaces perpendicular to the x direction are basically along this, there is no heat cannot cross, if I say that, then whatever the heat required along the stud should be given by the wooden sliding, it also should be taken out by this board. Okay. Which means the temperature present here will be different than temperature present here, right? Because there are two different Qs going. Is that
Right. That's correct.
correct? So
Temperature may be different.
temperature because there are two Qs going at different
Yeah,
sections of Q,
yeah,
which
yeah.
means it is no more isothermal along the sections. It's no more isothermal along the sections. So there's a
Yeah. Okay.
difference. Is,
Yeah,
is
yeah,
that
yeah,
clear?
yeah, yeah. Yeah, 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 yeah. Correct.
Right. So now if this is Q1, then the whatever Q1 stud requires, the same Q1 is given. Similarly, whatever the Q2, the insulation requires, the same Q2 is given on the wooden slide and wooden side and wooden board, wall board. So this also Q1, this also Q2. So now the current is or the heat is divided when it entered. So at this point itself, the heat is divided and it goes through in different sections. And when it goes through in different sections, the temperature, yeah, basically, what is this? The temperature here and here will not be same, even though it lies in the same plane. Now, now you can understand. Now, can you understand how the resistance changes?
Whether this temperature difference creates a heat transfer
It
in
will create.
in
It will create heat transfer, but what we assumed is it will be adiabatic. That was our
Okay.
assumption that we made. That was the assumption that we are asked to find for. So this temperature difference has to create heat transfer, but we are going to say that these surfaces will not conduct heat. There is no heat conduction. So which means heat cannot go in this direction, even though when there is a temperature difference. So this is an hypothetical scenario. In reality, it does not happen. In reality, everything is 2D. So this is an hypothetical scenario. I will tell you why we need to deal with this hypothetical scenario. Okay, but at this point, I hope it's clear. What is the difference between this approximation and the previous approximation? In previous approximation, we assumed that these 2 points are at same temperature, which means whatever Q enter has to go through all the wall and it has to go out. Then only we can assume it's the same temperature along the cross section, right? Now we say along the cross section heat will not travel, so these temperatures may not necessarily be equal. So what we can do is we can say it is an adiabatic, so we can say heat travels separately at separate sections. And when you do that, your resistance changes a bit. Your resistance starts from Ti, and then it initially itself divides, and then you have a stud, and then you have a wooden side. And the same goes on the Q1 and Q2 side. So now you might ask me, what is this stupid thing that we are doing? How can you say that, you know, when there is a temperature difference, heat is not happening? How can you make that assumption? This is a stupid assumption you can ask. So,
that can be still made, sir. Like kx and ky can be different. Ky is very
exactly.
less, then that can happen.
Wonderful, wonderful. So you made my job simpler. It can be so if it's not an isotropic, you can have this assumption. So usually why we do this kind of assumption is in some industrial applications we may not be able to nowadays. Computer is everywhere, so we can do CFD simulations or heat transfer simulations, and we can get how the temperature varies in a 2D or even 3D. But in previously, or if you want to quick calculations, if you want to do how the temperature varies or what is the maximum temperature I can reach, or what are the heat transfer analysis that I want to do, if I want to quickly calculate, and if you have this composite wall, and let's say you do not have a computer, then what you can do is you can make the first assumption that assuming it's isothermal everywhere, and you can find out what is the resistance, and you can make the second assumption and you can again find what is the resistance, and this is the maximum resistance that this kind of composite wall can produce. You can come up with a rough estimate. Okay, you can tell that this is the range of resistance in reality you will be able to see. So this is like exact 1D, and that is like very pure 2D. Okay, so or so if you say it's an isothermal everywhere, the heat has conducted along the um, along the y direction, or whatever this direction is, and this is more ideal case along the y direction. and this is more ideal case along the x direction, and in reality you are going to lie in between these two extents. Okay, so that's why in industry people usually do this kinds of assumption to come up with what is the range that we are dealing with. Okay, so for this we do this kind of approximation. So it's not totally wrong to do such an approximation. And also, as Mahadev Prabhu said, you can say that k along this direction is negligible. That assumption also you can take, and then you will be able to, and then still it will be valid. So this will give you a range of resistance what we are dealing with. That's why we do these two assumptions. Okay, so I hope I have justified why we need to do such a uh, why we need to solve such a problem. So you have this RWS1, RWS2. Now remember, RWS area is also different. Now whatever the area is going to be only for studs area. Okay? I hope that is clear. I am not going to solve this for you guys just for the sake of time. I am going to move on. I hope this is clear. If you have any doubts, feel free to ask.
So this RWS1, RWS2, why this S1 to that subscript came, I didn't get. I
Okay, so
didn't.
this corresponds to Q1 and Q2 basically. This is Q1, this is Q2, right? So
Right.
for Q1 you have only this portion. For Q2 you have this big portion. So ideally your area has changed now. So area here is this and this. This is for RWS1, and area here is going to be this, right? The difference in area. Are you able to understand now?
Okay.
Right? For Q1, what is the area it sees is now different. It's not the entire area now, right? So it's only the studs area, but in the wooden side. That's what it means. That's why we divided into two resistors. So now you do parallel for this. Now you do series for this first, uh, and then make this one resistance. You make the series, make this one resistance. You do parallel, then get the R resistance, and then divide it by 10 because you have 10 studs. And at the end, what you will get is, let me draw. Let me give you that also. Now R wall in this, let's say adiabatic, is going to be, if you divide by 10, you will get 0.18 Kelvin per watt. So basically you are going to vary from 0.1854 to 0.1888. Okay, so this will be the rough estimate of resistance that you are going to get in reality. So that's what that these are two extents of a reality. So you can get an idea that what is the resistance that we are dealing with. That's why we need to do such a problem. Okay, is that clear? So basically idea is we know how to make a thermal circuit, we know how to calculate resistance, and we know how to come up with the effective resistance. All right, I hope it's clear till now. I'm already past the 8 o'clock. Okay, let me quickly go through this problem also, and then I will leave you guys. Sorry for taking time. Now we have a nuclear fuel element of thickness 2L. Okay, this is the nuclear fuel of thickness 2L, and it has steel claddings. Usually fuels will have this cladding for the integrity, or to keep the fuel in the place, of thickness B. And you have heat will be generated in the nuclear fuel at a rate of Q and is removed by T infinity. Okay, and it is removed by this convection here at T infinity. Now, which adjoins one surface and is characterized by the convection coefficient H. Okay, the outer surface is well insulated, which means this surface is insulated. Okay, and then you have a steel, and then you have a nuclear fuel which is generating heat, and then you have a steel which is going to conduct that heat, and then you have a convection coefficient which is going to take away that heat. That is the flow process. It has thermal conductivity of Kf, Ks respectively. So this nuclear fuel is Kf and this is Ks. Now obtain an equation for temperature distribution in this nuclear fuel and sketch the temperature distribution for their entire system. Okay, we need to find how the temperature varies within the fuel. and we are going to assume it's a one-dimensional approximation. So along x only heat flows, and it is going to be uniform temperature along the area, along the cross-sectional area. So, okay, so let me write down assumptions. I hope I hope the question is clear for everyone. If not, please let me know. All right, so this is going to be 1D, and I'm going to assume it's in steady state. And what else I'm going to assume? I'm going to assume the constant case or constant. All right, we need to find t of x. What is t of x? How t of x varies, and we need to find the temperature distribution. You just need to plot the temperature distribution once you get the t of x. So how are we going to do it? It's a little bit different than our first problem, which also involves conduction and heat generation. But here we are going to have, but there they provided the uh, temperature distribution. Here we are going to derive our own temperature distribution. Okay. Heat generation rate is given, so we are going to assume it's a uniform heat generation. It does not vary with x. It's just a constant value, but it is constant for entire nuclear fuel, which is given as q. Let me write it qg itself so that I'm consistent, or q dot g, whatever it is. All right, so how do we do it? Same place we will start. uh, so whenever I say how do we do it, it's going to be energy balance. And in this problem we know it's a 1D planar steady heat conduction, so we can just start from heat conduction equation with heat generation, right? 1D steady heat conduction equation with heat generation. Okay, second. All right, now let's start from there. What is 1D steady heat conduction equation with heat generation? It's going to be T square T by dx square plus q dot g by k equal to 0. And this is true only if k is constant. Okay, so this is not true if the k is not constant, so please remember that. So we will start from here, and if you want to find t, what you have to do, you just need to uh, integrate this differential equation. So let's integrate it. I think we already partially did this in the class itself. Equal to minus q dot g by k, and we want to integrate it for the first time. It's going to be minus q dot g times x by k plus c1, and if you integrate it for the second time, the t of x is going to be minus q dot g x square by 2k plus c1x plus c2. Right, we already did this. Sorry. Yeah, now the question is we need to find the c1 and c2. Once we found c1 and c2, we are good to go. How do we do it? C1 and C2. So let's draw this here in a detailed manner.
I think we have to put the boundary conditions.
Right. So now I wanted to know from you guys what would be the boundary condition. So you,
Sir, one doubt, sir.
yeah, sure.
Compared to first question that what we have solved,
Hmm.
this question is different in a manner that here whatever heat is generated is only convected out from a single surface.
True.
In the first problem, we have the convection is from both surfaces.
True. Yeah. Yeah.
So this is not a symmetric problem. The first one was a symmetric problem.
That is also true. Yeah. It is not symmetric.
Okay, okay.
Wonderful. Good observation. We will see from the temperature profile. Finally, when we draw the temperature profile, whatever the deductions you made is perfectly. It's correct. So wait a minute. I don't know why I'm okay. So what would be the boundary condition? So we need to draw, as Basanchana said, we need to have boundary conditions. What would be the boundary condition? So you have K S here, K S here, and then we have this center line from which the X starts, and then we have Q dot G, and then thermal conductivity here is Kf, and then here we have H. Now you have X, and this is like how much L, and then you have B. What is the boundary condition? Where you will put the boundary condition is my question. This is also B.
On the left hand side, it is insulated, so there is no conduction out. So dt by dx should be zero, right, sir? On the left
Right
hand side.
here, is it
Yeah, yeah, on the left hand side.
like in this position? Uh,
Yeah,
is
yeah,
it
yeah, yeah. Yes,
this
yes, yes.
position heat conduction? Okay, so okay, that's a good point. Let's do that. This is at T at x is equal to minus L minus B, right? Minus L plus B, or you can write it as minus L plus B is insulated, which means dt by dx is 0. Dt by dx at minus s is 0 because it is insulated. Insulated, that is fine. Now, will you just apply this here? That's what boundary condition means. Why is he asking these many questions? Is your you know. So should we apply it here or no? I'm asking a lot of questions.
Yes, with different boundary conditions.
Yeah, that is what. So the reason why I ask is, so this is where I also do some mistakes. So you cannot directly apply this boundary condition here, although the boundary condition is right. Um, the reason is, whatever the this equation that you did for is a generalized 1D equation, but Q dot G is 0 in the in the steel. Steel is not generating what do you call uh, generating heat. Only nuclear fuel is generating heat. So whatever this equation that you have here is for temperature profile within the nuclear fuel, not outside the fuel,
Right, 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 sir, right, sir.
right? So but you have boundary condition here. Now you want to, can you find the boundary condition here? That's the question. Now you have boundary condition here. What would be the,
Minus L.
yeah, here, but what would be the boundary condition? Is this surface is also insulated? So question is, there is no heat generation here, okay,
Right.
and this surface is insulated, so there is no heat flux going out. So heat flux going out is 0 here,
Good.
right? And if this is the case, what would be the heat flux coming in? This is a steady state, right? If this heat flux goes out to 0 and there is no heat generation, the heat coming in should also be 0. Then only this can remain in steady state, right? If that is the case,
Yes.
if this is insulated, this is also insulated. No matter whether you have steel or whatever you have, if the material here is not generating any heat, then whatever the boundary condition here is also same as here. So actually, or in other words, I will say, in other words, what you can do, you can actually perform heat balance or energy balance for this steel. Okay, when you perform energy balance for this steel, heat is not generated. The energy in is, we don't know, but energy out is 0, we know. So for this steel in a steady state, E dot
N is zero.
in
N
is
is
zero
also zero.
basically. So if in is zero, then heat flux which is crossing in this direction is also zero. If heat flux is crossing is zero, it is insulated. If it is insulated, dt by dx is zero. That's what it means. So actually, this term can be translated to dt by dx at x is equal to minus L is also zero. This actually you can do by using energy balance at the steel. So it's a good practice. If you have time, you do energy balance, you will see for yourself that dt by dx at x minus L is zero. Now you are now the temperature profile is actually defined for nuclear fuel, and one of the uh, you know boundary condition which is insulated, which is dt by dx is minus L. Now you can substitute this in the equation. So let's say this is 1, substitute in 1. Okay, now what will happen, you can differentiate it once, or we already did dt by dx is this thing. So this is going to be minus q dot g L by k, right? K here, k is k fuel. Okay, stop, forgot that. So that is also one thing you need to know. We have two k's, but we didn't discuss that when we first derived it. Okay, so this is also one of the reason why we need to say why this equation is applicable only for nuclear fuel, not to the steels. Okay, for the steel we need to find out temperature profile separately. Okay, all right. What I'm going to do, plus c1 equal to 0, this is equal to 0, and yeah, x to be minus L. So if you substitute minus L, then it becomes qg times minus L. So this becomes C1 is equal to minus Q dot G L by K. So we found the C1. Now we need one more boundary condition. How do we get the other boundary condition? Now there is no other option. We have to use another energy balance basically for the other side, right?
Yes.
So basically here the heat flux crosses will be 0, we know. So we need to know what is the heat flux here. The whatever heat flux comes out is nothing but the conduction in the steel, and whatever the conduction in the steel is nothing but the convection to the environment,
Right.
right? So actually you can do a equivalent resistance for K and H, and you can find the resistance, and then you can find the Q, and you can match that Q to this Q. That will be your another uh, uh, boundary condition. Okay, so let's see, this is steel, this is Q flux coming in, this is x is equal to L, this is x is equal to L plus P, and then you have airflow with H. Now what would be the Q coming in, which will be nothing but let's say this is Ts and this is T infinity, which will be nothing but Ts minus T infinity divided by R conduction in the steel plus R convection, right? So if I want to write this is Ts minus T infinity divided by conduction is K steel, sorry. So L steel is going to be, so just the width of this steel is B. So B by K steel times area plus 1 by H times area. Now let's say you wanted to write uh, Q is equal to, you can write this as area times Ts minus T infinity divided by B by Ks plus 1 by H. Areas are going to be same basically. Is that clear?
Yes, sir.
Now this part at x is equal to L. Now coming back to the nuclear fuel, at x is equal to L, whatever the heat comes to this is going to go out, right? So let's say this is your surface, whatever heat comes is going to go out,
Stay.
right? Or what you can also do is you can apply, like we discussed before, this whole nuclear fuel, you can apply energy balance. Whatever Q generated is going to go out, right? So let's say we apply that. Okay, this is the nuclear fuels energy balance. Now, whatever the heat generated, nothing can go to the other side because it's already insulated. So whatever heat generated has to go out through the steel and edge. And we just found the heat crossing the steel and edge. And I'm going to say this A times Ts minus T infinity divided by B by Ks plus 1 by H is nothing but Q dot generated times A times 2L, right? Volume is 2L times T. Volume is 2L times A. This is what these two. So this is again same energy balance like we discussed, like our first problem. Now, what are we doing here? We need to find out uh, a boundary condition at x is equal to L. And what is your boundary condition here at x is equal to L? So T at x is equal to L is nothing but Ts, right? That's what it means. T at x is equal to L is what Ts. That's what we are trying to find out. This Ts, we now have an expression here. How you can write this? Ts is nothing but area, you can cancel on both sides. Now you can write this as T infinity plus Q dot G times 2L times P by Ks plus 1 by H. So now we have boundary condition. This is Ts. So now you have equation T of x. Now you substitute the C1. We need to substitute C2, right? So T at x is equal to L is nothing but minus Q dot G. X square will become L square divided by 2kf plus C1. C1 is minus Q dot G L by K minus Q dot G L by K F times X. X is nothing but again L. Now plus C2 is nothing but Ts, which is going to be T infinity plus Q dot G into 2L times P by Ks plus 1 by H. I know this is becoming very long, so maybe I will quickly give you the C2. You just need to rearrange this. Once you rearrange, you will end up having T infinity Q dot L 2B by Ks, sorry, 2B by Ks plus 3L by 2Kf plus 2 by H. This is your C2, and what you do, you substitute everything in one single equation and you will have Tx to be minus Q dot G x square divided by 2 times Kf minus Q dot Lx divided by Kf plus Q dot GL times 2B by Ks plus 3L by 2Kf plus 2 by H plus T infinity. Okay, so this is how you derive it. In the first equation, we are lucky they already gave the uh, temperature expression, but it takes this much mathematics to derive it. And one more thing is, in the first problem, I think that is almost equivalent to your assignment to problem. So I that's why I took the first one to show you how to do it. But this is how you actually derive the temperature profile, and this will give you with this you can actually plot the temperature distribution. Now that is the fun part here. So let's say if this is the equation and if this is given, or let's say we derived it. So of course we derived it till here. So if you just if you take C2 on this side and T infinity Q dot L by, I took the 2 inside, and then these two simplifies to 3L by 2 KF on this side basically. So I just simplified it and wrote it. Uh, and finally you have this equation. Now if you want to draw, we are also asked to draw, asked to sketch the temperature profile. So let's say if we want to do that, how do we do that? How will the temperature profile looks? Now, okay, since x is in the middle, what I will do is, this is our temperature axis and this is our x axis. Okay, this is minus L, this is plus L, and this is minus L plus B, this is plus L plus B. Okay, now how would the temperature profile look? Any idea? We have to use all the information that we have. Let's start from the insulated wall. Insulated wall, we know the temperature gradient is 0. That was one of the thing, right? So okay, I'm going to ask simple questions. Let's not dive into too much. Let's say we have this
Parabolic, on-symmetric parabolic.
one parabol. Yeah, it will be parabolic because we have x square. That
On
will
sim,
be
but it would be on-symmetric.
on symmetric means what do you mean by that?
Means to the left side, I think since
Left side you will
that's
have parabolic.
both the side will be parabolic having the central point, the maximum one,
Hmm.
nuclear fuel.
Maxima will be at the other end now, minus L, because
Mm,
temperature, the dt by dx is 0 over there.
right, right. If we
Maxima should be on the other side.
right. So what? Yeah. So here it cannot be parabolic, especially on the left hand side. And as Mahadev said, it is going to be uh, what do you call temperature gradient is 0. And if you think about it, you are generating heat here, and the heat is going out only in this direction, which
Yes,
means
yes, yes.
which place will have maximum temperature? If you think that, will it be in the center?
I
No.
think that because the heat is generated in the fuel rod.
Yeah, heat is generated here, right? Heat is generated throughout this fuel.
Yes,
So ideally, if the no heat goes out, then everywhere the temperature will be very high. Okay. Now what happened is only one side you are removing heat, right?
right.
So that
Hmm.
doesn't tell that the temperature should be maximum at the center, right? So if you have a heat removing in this side also, if the heat is removed in this side also, then as you said, the temperature will be maximum here. But heat is not removed this side. Only one side heat is getting removed,
Okay, okay, right.
right? So which means the whatever the heat generated here, there is only one side it can go. It cannot go this side. So the heat generated at this point, the heat generated at this point, heat generated at this point, or to the far end of the nuclear fuel, can only go towards right. It cannot go towards left. And if it has to go towards right, the temperature on if it has to go through the what should be the temperature should be lower to the right,
Yes, exactly. Lower
right?
to
Then only heat can
higher,
transfer.
higher in left side and lower in the right side.
So whatever heat is generated here, if it has to go through here, then temperature here should be lower. And if the temperature here lower, here is only you can have max.
Max,
That's
yes,
what
yes, yes.
Mahadev
Yes,
Prabhu was telling. So if you have max here and steel is, not doing anything, so heat flux is zero over steel, then the steel is also at maximum temperature, which means till
yes,
from the insulation wall till the steel end, this is what the maximum temperature, and it is going to be straight line, which means dt by dx is zero there, right? All right. So this is going to be T max. This is steel and this is nuclear fuel. So it is going to be straight line from here to here, and it is going to be maximum at this place. Now, as you said, it is going to be parabolic. Okay, and it is going to be parabolic to Ts, and Ts is going to be certainly less than T max. So let's say I am putting somewhere here Ts. Okay, so at this point, let's say my temperature is Ts, and I am going to have parabolic profile. It's going to be something like this. Okay, now what is going to be in this side steel? How it is going to be the profile?
I think still it is because of conduction, so it's will linear one.
Exactly, wonderful. So it is going to be linear. So since because here it's a conduction, it is going to be simply linear profile depending upon the thermal conductivity and things like that. And then what will happen? And then you have convection. How will that profile look? We haven't discussed that much.
Yes,
So it is going to look something like this. It's a very different profile. It's a very smooth profile. You will come to know why we draw always the convection like this. We do not follow any parabolic, or we do not follow straight line or something, but we suddenly drop the temperature to T infinity, and we will say it is reaching like this. Okay, you will soon learn this why we are drawing this in the while we are studying convection. Basically this drop in temperature happens within the boundary layer. That's what it means, and the boundary layer is very thin, and so there will be
the
a
gradient
sudden
is high. The gradient is very high.
gradient is very high. That's why we have sudden drop in
Yeah,
temperature,
yeah.
and it quickly reaches T infinity. That is because it's a convection ocean. So this is how your temperature profile looks. Okay, and actually you can find this T max by differentiating this T of x equation, and you can make them equal to 0, and you can find this T max and the other Ts, everything you can find given q dot g, k, l, h, all these things. If it is given, then you can find them. Actually there is a I think there is a continuous problem for this where q dot g, k, and s are given in the Incropera book. In the next problem for this, maybe you can use that, and then you can find out what would be the temperature profile in kelvins and degrees Celsius. Okay, so that is all I have, and I took all the time. I'm sorry about that. And if you but anyway, I will be available if you have any questions to ask for. And I hope this three questions is helpful, not just in terms of understanding, not just in terms of solving the uh, assignment problems, but is also in terms of understanding uh, the certain concepts such as energy balance and things like that, and how will you approach the problem. So that's the idea I had for you to show today. If you want something else, or if you want me to change the way I'm uh, teaching, please let me know. If you want me to speed up the process, please let me know. If you want more questions also, let me know. I can do it. But if this is fine, that is also fine. Let me know what you guys prefer, and based on that, I can adapt.
Sir, I have one small doubt
Sure, sure, please.
regarding the same last question.
Okay.
On the left hand side, even though with the insulation, we
Mm-hmm.
have considered there is no heat transfer even from minus cell surface. Minus cell surface, we don't have any heat transfer.
Right.
We considered that because this is not an unsteady problem.
Yeah, exactly. Yeah,
So,
exactly.
just because of that assumption, we put that, or in actual case, in actual practice, it holds. Because
Yes.
why that question I asked is because that surface is always in contact with the fluid which is generating heat. Still, you have Q equal to zero, which means the conductivity of that steel should be very low, so that Q can be zero. But that won't happen.
So, yeah, this is okay. Yeah, yeah. I understand your question, why it is coming. So, this is because, as you rightly said, it is because steady state. Let's say how it will evolve as a, you know, if initially how it will be is, initially, let's say nuclear fuel is not generating, then initially your profile would look something like this. It's just a straight line. It would be same as T infinity. Okay. Now once let's say nuclear fuel starts generating heat, what happens is, since it starts generating heat, you will have a temperature will be high, and there will be something, and then there will be going something like this, and then there will be something, and then there will be, so it will start forming this kind of temperature profile, like parabolic profile, with maybe with uneven temperatures from left and right hand side, and it slowly reaches the steady state. And when it reaches steady state, whether steel has any thermal conductivity doesn't matter, since heat cannot go this side, it cannot have different temperatures, it will have same temperatures, because whatever comes out is fully insulated. I made sure that I'm insulating this fully. So whatever comes out in this direction is what, nothing can go out in this direction. If nothing can go in this direction, nothing can go in this direction.
But it can still store heat, right? But it
Yes,
can
can
still
store
store
heat.
the.
Yes, can store heat. Steel can store heat. If it is an unsteady, that's what it is doing. So at time t equal to 0, it is 0. And then as time increases, it stored this much heat, right? As it goes, it stored this much heat. And once it stored this much heat, whatever the generated has matched the, whatever the heat you generate here, whatever the heat you generate here as is match the convection coefficient here, or match the convective heat transfer here. So there is no heat that need to go this side. So since heat generated has matched the convection, so whatever the heat stored stays there as heat, stays there as energy.
Accumulates. It accumulates there.
Heat accumulates. Heat started accumulating, and at steady state, it that's all it can do. It cannot have. It cannot store any more heat. I mean, it can store any more. It can store more heat, but provided it has to increase the temperature. So once it reaches T max, it will not store any more heat, because none of the heat is going to it. Not because it is not storing it. None of the heat is going to it, because all the heat is going out.
So what is the upper cap, sir, for storing the heat? What decides? Okay, this
Ex-
much only I can hold.
Yeah, the upper cap actually it has nothing to do with the steel. It has to do with the convection. Now, if when you increase the convection, the more heat you can remove it, the lesser the T max will be. Okay, there is no upper
Okay.
cap for steel. Steel can reach minus 6,000. I mean, of course, its integrity will be gone. It cannot remain as a solid. uh, but let's say you this steel is some hypothetical steel, and it can still remain as solid, and it can reach if it can remain as a solid, it can reach any T max. Doesn't matter, there is no upper limit for storing the heat. However, the upper limit is on how much you can remove the heat, because this is continuously going to generate. If the Q generator generation is fixed, that much heat you have to remove it. And if the Q generation increases without increasing the convection over here, this will reach to increase in Tmax.
Okay. Okay.
Did you understand or did I confuse you?
I didn't understood how this heat transfer coefficient or the convective heat transfer coefficient is going to give an upper cap on the storage of steel, storage of heat.
Okay.
That
Okay. Um,
I'm sorry
so
for
yeah,
taking
no,
more
no, no,
time.
no, no, no. No. Uh, that is fine. That is fine. I took a lot of time today actually. So anyway, see, one thing is whatever the heat is generated, it has to go out by the convection. Now, if the okay, in other words, let me explain it in a different way. So now you have a nuclear fuel generating heat, and now uh, let's say you put an insulation here also. Let's say you put an insulation. There is no way heat is going out. Now, what would happen? What do you expect? There is this
The
heat,
temperature will rise
temperature will
continuously.
rise. This T max you have will continue to increase. It will continue to increase. It just keeps on increasing.
Yes, yes,
It
yes,
is no more a steady state problem because
yes,
there's only generation coming, but there is nothing removing it. So it will not be steady state. It will be keep on storing the heat. That is clear.
yes,
Okay.
yes, yes, yes.
Now this QG you have. Let's say you remove this insulation. Okay, and then you put some convection. Q convection.
Okay,
Okay, you put some Q convection. Only little bit Q convection.
okay.
Now what will happen? The Q generator Q generated has to go through this Q convection.
Yes,
So
yes.
until uh, the temperature profile here matches the Q convection, it will keep on increasing the temperature here. So once this Q generator is equal to Q convection, there will not be no more increase in Tmax because that is what a steady state is,
Mm-hmm.
right? Then now you can either say this Q generation. So the answer to your question is when you match Q generation with the convective heat transfer, QHT, convective heat transfer. So when you match them, whatever the temperature you get will put the highest limit. So which means what is going to put you the highest limit? Which means the convective heat transfer coefficient, K of the fuel, and probably Ks also. Yeah,
Mm,
probably
yes.
Ks also. Right. So at the end of the day, what is influencing is so, or in other words, let's say we define you have Q dot G. Now, for now, let's say this is the T max. Okay. So T max 1. Now you reduce the Q dot G by half.
Okay.
Okay. So once you reduce the Q dot G by half, what will happen? Let's say if you want to reach the steady state, again you will reach the steady state. This Q dot G by half will be, you have to equate it with the Q convection, and once you have this Q convection and then once you reach the steady state, okay, will the T max will it be same as T max 1 because you have reduced the heat generated.
Then it should reduce. No?
T max also reduces. So
Reduces.
basically, exact. So basically, maybe what I'm trying to say is this convection, when the convection matches Q dot generation, that is when you get T max, and the parameters which are going to affect is your heat transfer coefficient and your K of fuel, also K of, yes, steel, because you have steel here and then you have H here.
So whatever heat generated, it is taken up by the air.
Mm,
Then Tmax, it will remain as Tmax, and the stored heat will be as such.
right,
As such.
right,
Okay.
true. So Yeah, yeah, that is right. You're right. So, but initially, yeah, this is how it starts. Initially, it will be zero everywhere, and then it slowly, continuously increases on the other side, and you know, it forms this kinds of profile at the steady state.
Yeah.
That's how
Fine.
it is.
Fine. Fine. Thank you, sir. Thank you, sir.
All right. By the way, you guys no need to call me sir. You can just call me Ganesh. There is no problem. I'm also a PhD student, so it's fine. Thanks for staying back and thanks for asking questions. If you have any more questions, I will be happy to answer even for another 10-15 minutes. Please let me know. If not, we will meet again in week 3. Okay.
Thank you, sir.
All right. Thank you, Basan Chena. Thank you, Mahadev. And thank you, all the other joinees who joined today and also the people who are going to watch in YouTube.
Thank you, sir.
All right. Thank you. Good
Thank
night.
you.
Thank you, sir.
Bye.
Good
Thank you.
night. Good night.
Good night. Bye bye.